Hey folks, welcome to another set of Chemistry 2 video notes. Today we're going to be covering Chapter 12, which is all about solutions. In this chapter we discuss what a solution is, how energy plays a role in the formation of solutions, how entropy plays a role in the formation of solutions, how solubility is related to temperature and pressure, how to quantitatively describe the concentration of a solution using molarity or percent composition, and the colligative properties of solutions. While this is a rather long-looking chapter, I strongly suggest you take the time to read it. The authors do a wonderful job of explaining and illustrating the why behind many of these concepts. Unfortunately, in this shorter video, I don't have time to describe everything as well as the book does, so you're going to get the skinny version here. That's a lot to cover, so let's get started. As you may recall from Chapter 1, a solution is a homogeneous mixture of two or more substances. By homogeneous, we mean that the solution is the same throughout. For example, if I dissolve some sugar in some water, every tiny volume of the solution would contain the same amount of sugar molecules dissolved in the same amount of water molecules. Another way to say that is that the concentration of the solution is the same throughout. All solutions are made up of a solvent, which is the substance in the solution that accounts for the most volume, and the solute, which is any other substance that's mixed in with that solvent. Another way to think about that is that the solute is what is being dissolved, and the solvent is what is doing the dissolving. In our example of sugar water, the sugar would be the solute, and the water would be the solvent. We can form solutions in any state of matter. For example, an alloy, which is a mixture of different metals, could be considered a solid solution. The air we breathe, consisting of 78% nitrogen gas, would be considered a gaseous solution, with nitrogen as the solvent, and oxygen, carbon dioxide, and other gases as the solutes. Most of this chapter and most chemistry that we do deals with solutions in which water is the solvent. These are called aqueous solutions, which you have already dealt with when assigning state symbols back in Chapter 8. Liquid water is often known as the universal solvent because it dissolves so many different substances with ease. Water is a particularly great solvent because of its high polarity and hydrogen bonding. Having those large partial negative and positive charges allows water molecules to attract to other molecules, either to other molecules of water or to particles of a solute. Think back to when we talked about bonding. Sodium chloride, common table salt, is a crystalline structure held together by extremely strong ionic bonds. What's so special about water that allows those ionic bonds to be broken so that salt dissolves in the water? To best understand that, we have to think about the dissolution of sodium chloride as happening in three different but simultaneous steps. In one step, the sodium chloride crystal structures have to be broken apart into separate sodium and chloride ions. This is called the solute separation step because the solute gets separated. Since we're breaking bonds, this step requires an input of energy. It always takes energy to break bonds. Remember, water molecules, being highly polar, are very attracted to each other, which leaves little room between them. In order for the water molecules to attract the positive and negative charges of the sodium and chloride ions, they have to move out of the way to make room for those ions. This is called the solvent separation step, and it also requires an input of energy since we're breaking attractive forces between the water molecules. Thirdly, and still at the same time, our sodium and chloride ions can fill the gaps between the water molecules. These open spaces between the water molecules are known as solvent cages. For a positive sodium ion, the solvent cage will consist of a number of water molecules with their partially negative oxygen atoms surrounding it. For a negative chloride ion, the solvent cage will look similar, but the partially positive hydrogens of the water molecules will be surrounding the chloride ion. Remember, opposite charges attract. The attraction between the ions and the polar water molecules is known as an ion-dipole attraction. Since this time we're making attractive forces instead of breaking them, we release energy in this step. Since solvent molecules surround our solute particles in this step, we call it the solvation step. For this particular example, or any example in which water is our solvent, we can also call it the hydration step. So the energy released when this step occurs can also be called the hydration energy. So how do we know if a solute will dissolve in a solvent? Simply, the amount of energy released by the solvation step must be enough to cover the energy required for the two separation steps. In order to determine whether a solute will dissolve in a solvent, we have to think of the overall change in energy, or the delta E. When we add energy into a system, the change in energy is positive because the energy of the system increases. When energy is released from a system, the change in energy is negative because the energy decreases. With that information, it should be obvious that for the solute separation and solvent separation steps, the delta E is positive, and for the solvation step, the delta E is negative. The total change in energy can be expressed as the sum of these three energies. In general, when the total delta E is negative, that means we had a net release of energy, and our substance will dissolve. In other words, the energy released by solvation was more than enough to make up for the energy required for the two separation steps. When there's not enough energy released by solvation to cover the energy required for separation, the total delta E ends up being positive, and then the substance is less likely, or probably won't, dissolve. In general, like substances will dissolve other like substances. In the case of sodium chloride and water, we had sodium chloride, an extremely polar, so polar it's ionic, solute, dissolving in a very polar water solvent. What if we were to put sodium chloride in a nonpolar solvent, like carbon tetrachloride? Remember that Coulomb's law states that the attractive forces between two charged objects are higher when the charges are greater, and the distance between them is smaller. It takes a lot of energy to overcome the ionic attraction between fully positive and negative sodium chloride ions. It takes little energy to overcome the London dispersion forces between the nonpolar carbon tetrachloride molecule. Remember, nonpolar substances don't have any permanent partial charges on them at all. So any attraction between carbon tetrachloride and sodium and chloride ions in the solvation step will not be nearly as strong as when the solvent was water. In this case, the energy released in the solvation step, because we formed very weak attractions, would not be enough to supply the energy required to break our solute and solvent particles apart. Therefore, sodium chloride does not dissolve in carbon tetrachloride. What if I try to dissolve some nonpolar solute in this nonpolar solvent? Well, the energy required to break the nonpolar solute particles away from each other is significantly less than the energy required to break apart sodium and chloride ions. Since this requires less energy, it's much more likely to dissolve. In fact, since both separation steps and the solvation step only involve breaking or making very weak London dispersion attractions, the overall change in energy will be very small for any nonpolar solute dissolving in a nonpolar solvent. Even if the delta E is positive, this is likely to dissolve. Why? Because of entropy. What is entropy, you ask? I like to think about it as the degree of randomness that's present. The more order you have, the less entropy you have. Another way to think about it is that when the entropy increases, the probability of this particular situation happening increases. The analogy of entropy in your textbook involves laundry. If you fold your laundry and color organize them in specific drawers, that has a very low amount of entropy because it has a lot of order to it. There's only one specific way that you would put your laundry away each time. However, if you're in a rush and just throw your pile of clean laundry at your dresser instead of folding them and putting them away, there's an infinite number of possibilities for how those clothes will be arranged. This has extremely high entropy. So the two factors to take into account when determining if something dissolves is the overall change in energy, also known as the enthalpy, and the overall change in entropy. The goal of any physical or chemical change is to decrease the enthalpy, or energy of the system, and to increase the entropy, or the randomness. Think back to our sodium chloride as a solid. It's in a highly ordered crystal lattice structure. It does not have a lot of entropy. When it dissolves, the entropy increases because there are many more possible arrangements of the molecules. These possible arrangements are known as microstates. The same is true of any dissolution. This explains why, even though in the dissolution of a nonpolar solute in a nonpolar solvent gives a small overall increase in energy, or a positive delta E, the substance still dissolves. The great increase in entropy makes up for that. If it helps to remember it in an equation form, the Gibbs free energy, or the delta G of a process, is equal to the change in energy minus the temperature times the change in entropy. Processes only ever occur spontaneously when there's a negative value for delta G. This always happens when delta E is negative because two negatives add together and will always be a negative. For dissolutions, the change always occurs when the delta E is negative, because the negative delta E minus the entropy change is always going to give us a negative Gibbs free energy. This can also happen when the temperature is high enough or the increase in entropy is high enough to overcome any positive delta E value. When you move on to AP chemistry, we'll talk a lot more about enthalpy, entropy, and Gibbs free energy. For now, the bottom line that you need to know is that a decrease in energy or an increase in entropy are usually favorable spontaneous reactions. If the energy increases or the entropy decreases, those reactions are usually unfavorable. As you might have noticed, that little equation I just threw at you included temperature. That temperature value is attached to the negative change in entropy. This should conceptually make sense. If I try to dissolve a lot of sugar into a glass of water at room temperature, it'll dissolve up to a certain point, and then I'll still have chunks of sugar left at the bottom of my glass. As I warm my water up, more sugar is able to dissolve. This is why the temperature is attached to entropy in that equation. In general, for molecular solids like sugar, as temperature increases, so does the amount of the substance that I'm able to dissolve. This is because the higher the temperature, the more negative my delta G becomes. The same is true for most ionic solids. The solubility of a substance is defined as the maximum amount of solute that can be dissolved in a certain amount of solvent. Generally, we report this in grams of solute per 100 grams of solvent. As you can see in this chart for sugar solubilities, as the temperature increases, I'm able to dissolve more and more of my sugar in the water. For gases, the story is quite the opposite. As temperature increases, the solubility of gases decreases. To remember this, just think of soda. As it gets warm and sits out, the carbon dioxide that's dissolved in the soda is more likely to escape the solution, causing your soda to be flat. Pressure also affects the solubility of gases. The higher the pressure of the gas, the higher the solubility. This is known as Henry's law. To remember that, think about what pressure is. The higher the pressure, the more the particles are moving and hitting the walls of the container. You could think of the surface of your solution as the bottom wall of the container. As the gas particles hit the liquid surface more often and with more force, they're more likely to be captured by the liquid and dissolved into solution. In either case, once we've hit the maximum amount of solute that can be dissolved in a solvent, we call our solution saturated. An unsaturated solution would be any solution that has less than the maximum amount of solute dissolved in it. We could continue to describe our solutions based on how many grams of solute are dissolved in a certain amount of solution, but for chemical reactions, it's best that we converse in terms of moles. In any case in which we're talking about an amount of solute per an amount of solvent or solution, we're talking about the concentration of our solution. The most commonly used, and in my opinion, most useful way to discuss concentration is with molarity. This is how many moles of our solute are dissolved in 1 liter of our solution. There are 2 basic ways to prepare a solution with a certain molarity. If we're preparing a solution from scratch, we need to know how many grams of solute we need. Say we want to make 250 milliliters of 1.5 molar solution of sodium chloride. To do so, we'd use dimensional analysis. Start with your desired volume of 250 milliliters, convert the milliliters to liters. Then we can use molarity as the conversion factor because we know that we want 1.5 moles for every 1 liter. Once you do that, you figured out how many moles of NaCl you want. Use the molar mass to convert that from moles to grams. According to my math, I'd need 21.9 grams of NaCl dissolved in 250 milliliters of water. To do that, I'd simply measure out 21.9 grams of salt, add it to a 250 milliliter volumetric flask, and fill that flask with water up to the line on the neck. The other way to prepare a solution is from a stock solution, or another solution of known concentration. This actually starts out the same way. Say I had a 5 molar sodium chloride solution already made up, and I wanted to dilute it to make the same solution that I just made. Start out with your desired volume, convert to liters, and use molarity to convert to moles. If I know how many moles I need, and I know that for every 1 liter of my stock solution, I have 5 moles, I can use that molarity as a conversion factor to find the volume of stock solution I would need. In this case, I would need 0.075 liters, or 75 milliliters of stock solution. I'd measure that out with a pipette or graduated cylinder, pour it into a 250 milliliter volumetric flask, and again fill it with water up to the line. A shortcut method to doing this math is M1V1 equals M2V2, where M1 and V1 might be the molarity and volume of your stock solution, and M2 and V2 would be the molarity and volume of your desired solution. This is known as the dilution equation. The desired solution I'm trying to make has a concentration of 1.5 molar and a volume of 250 milliliters. The stock solution I have has a concentration of 5 molar. To find the volume of stock solution I need, I'd simply solve for V2 and get 75 milliliters, the same as I did before. It's actually the same exact math, it's just a shortcut method to do it. Another useful and common way we express concentration is by percent composition. The 3% compositions you may see are percent composition by mass, which is grams of solute divided by the grams of solution times 100. The percent composition by volume, which is the volume of solute divided by the volume of solution times 100. And the percent composition by mass per volume, which is grams of solute divided by volume of solution times 100. If you prepared your solution by dissolving a solid into a liquid, you're best off describing the percent composition by mass. When your solute is a liquid, it's best to report it by percent composition by volume. No matter the case, we can use percent compositions as conversion factors as well, because it tells us what amount of solute is in a certain amount of solution. When you buy solutions in the store, you tend to see percent compositions, often by volume, reported. When reporting any of these compositions, it's important to specify whether it's by mass, by volume, or by mass per volume. We do that in order to make sure the reader understands the units that you're using. At any rate, as chemists, we still tend to stick to molarity because it gives us the most useful, most consistent, and most easily usable information for when we do stoichiometry calculations. Speaking of stoichiometry, now that we know what solutions are and how to describe them, we can put that knowledge to use to describe chemical reactions that happen in solution. In short, your methods for stoichiometry are exactly the same as they have been. The only difference this time is that we've added a new conversion factor for your toolbox, molarity. If you have a molarity, you can convert either from liters to moles or from moles to liters. Look through examples on pages 478 and 479 of your book to see those conversion factors in action. This becomes useful especially when performing titrations. Titrations involve adding a known volume of a solute with known concentration to a known amount of solution with an unknown concentration. This most often occurs with acid-base neutralization reactions, where we add just enough of a known concentration of a base to react in stoichiometric or balanced fashion with our acid. The acid, of course, we don't know the concentration of. In doing so, and with a little bit of stoichiometry magic, we can calculate the moles of the base that we used, convert that to how many moles of acid that must have been in our unknown acid solution, and then find the concentration of our acid by dividing by its known volume. Titrations are extremely common and important processes. Check out the example on page 482 in your book to help you better understand the steps we take mathematically when performing titrations. Finally, let's talk about the colligative properties of solutions. It might be best to think about the properties of pure solvents before discussing the properties of solutions. As you know, pure substances have distinct freezing and boiling points. As you may also know, while a substance is freezing, melting, boiling, or condensing, it stays at that temperature until the phase change is complete. We can see this graphically on a heating curve much like this one. Vapor pressure, however, may be new to you. A liquid can enter the gas phase without boiling. You see this all the time when water evaporates from a puddle. This is due to the liquid's natural urge to enter the gas phase. We can measure this by placing a small amount of liquid inside of a sealed flask that has had all of the air removed from it. Eventually, the water will leave the liquid phase and turn to a gas. Adding more gas particles will increase the pressure. The pressure will continue to increase up to a certain point. That point in which the pressure no longer increases is known as the vapor pressure for that liquid. Why does it no longer increase? Well, at that point, the pressure is high enough to force some of the gas particles back into the liquid phase. The rate at which the liquid particles are turning into a gas and the gas particles are turning into a liquid end up being the same. We can write this as a single equation where liquid water turns to gas water, but the gas water also comes back to the liquid state. We show this by putting a set of two arrows instead of a single arrow. Those arrows represent the forward and reverse reactions, liquid to gas and gas to liquid. When the rates of the forward and reverse reactions are equal, we call this situation a dynamic equilibrium. Dynamic to remind us that things are changing They're just changing equally in either direction so that it looks to us like nothing is changing. Vapor pressure is a function of temperature and will always increase as the temperature increases. In an open container, a liquid will boil as long as the vapor pressure is greater than the atmospheric pressure. At sea level, the atmospheric pressure is 760 millimeters of mercury. At 25 degrees Celsius, the vapor pressure of water is only 23.76 millimeters of mercury, so it doesn't boil. Even at 70 degrees Celsius, the vapor pressure of water is only 233.7 millimeters of mercury. It's still not enough to meet that atmospheric pressure. It's not until the water hits 100 degrees Celsius that the vapor pressure is equal to 760 millimeters of mercury. At that point, the water is now able to boil. This also explains why, at higher altitudes where the atmospheric pressure is lower, water is able to boil at lower temperatures, because the required vapor pressure is also lower. Finally, let's talk about the colligative properties of solutions. A colligative property is a property that depends on the amount of solute dissolved in your solution. The identity of the solute does not affect these properties, only the amount of solute. When you add a solute to a pure solvent, the boiling point always increases, the melting point always decreases, and the vapor pressure always decreases as well. These are known as boiling point elevation, melting point depression, and the lowering of vapor pressure, respectively. We can calculate the amount our boiling or freezing points will change using these two equations. In these equations, Kf and Kb are the freezing point constant and the boiling point constant. In either case, we multiply our constant by the moles of solute particles per 1,000 grams, or 1 kilogram of solvent. This tells us how much our temperature will change. If we're looking at the change in boiling point, we will add that to our normal boiling point because the boiling point gets higher when you add a solute. If we're looking at the freezing point, we'll subtract the change from the normal freezing point since the freezing point gets lower. Well, that's all for today, folks. I know that was a lot to get through and a lot of new stuff, so hopefully this video helped at least a little. As I mentioned a few times, I would definitely take the time to read this chapter, or at the very least, look through the example problems and work through some of the practice problems on your own to get a good feel for this step. As always, let me know if you have any questions.